Right, so in this video we're going to look at the theory of indices, and we're going to have some fun with some numbers at the end of this little section. But first of all, we're going to look at the algebraic ideas behind working with indices. So first of all, let's have a look at something nice and simple, like any number a to the power, well, let's say 5. So a to the power 5, of course, is a times a times a times a times a. So that little power there, the index as we call it, the index, the number of the index gives us the number of times a is multiplied by itself. An important point here actually is that if a was to the power 1, then of course, so a to the power 1, then of course there would be just one of these. So anything to the power 1 is just itself, and we just don't bother with the 1. So let's first of all work out what the laws of indices, so-called, are. And these are to do with when you multiply and divide bases, as they're called, and indices together. So say you have something, for example, like a squared, which of course is a times a. If we multiply these together, then you're going to have a times a times a times a times a times a times a. In other words, you're going to have a, let's write it down here, a to the power 5 times a squared is going to be a to the power, so on, 7 times. So you're going to have a to the power 7. And this is an important finding. It gives us law 1 of our rules of indices, which is that when we're multiplying the bases, we're adding the powers. So a common misconception here is that you times the powers as well as you times the bases. So you just look at that times sign, and students who don't understand this, they just go 2 times 5, which gives them a to the power 10. But no, you add the powers when you multiply the bases. So law 1 can be expressed algebraically like this. A to the power, let's use a letter from the middle of the alphabet, any number m then, times a to the power another number, let's say n, will give you a to the power not m times n, but m plus n. So you add the powers. So law 1 says that you add the powers. And I'll just write add here for short. Okay, so what would happen then if we divide the powers instead? So divide the bases rather. So if we look at a division, so that instead of a to the power 5 times a squared, we have a to the power 5 now, divided by a squared. Well, a good way of looking at this would be, let's just draw a line underneath here. So this would be our fractional bar, which of course is another division symbol. And so now we've got a times a times a times a times a divided by a times a. Well, we know that with fractions we can simplify fractions by dividing the top and dividing the bottom by the same number. So if we divide the top by a, we'll have a divided by a, which will just give us 1. So we can cancel this, do the same to the bottom, cancel top and bottom. So we simply have 1 now times a times a times a times a, and 1 times a at the bottom, giving us simply a times a times a divided by a. And we can do the same again to these. We can cancel top and bottom, so that we now just have 1 at the bottom here. And so our result would be, if we write it out here, a to the power 5 divided by a squared gives us just a times a times a, which is a cubed. And again, really important result. We can see what's happened. We've subtracted the powers then. So when we divide the bases, we subtract the powers. So law 2 is that when we have this situation, a to the power m divided by a to the power n, we simply subtract the powers. So it's a kind of the opposite or reverse operation to multiplication. So that we call the second law of indices, and for short I'm just going to write it's when we subtract. Okay, now moving on to the third law. This is when we have something quite interesting going on. So if we have a to the power 5, let's just erase these so that we can see it nice and clearly. And this time, there we go, we're going to raise all of this to a power. So again, let's use this idea of squaring. So squared. So whatever is in the brackets, in this case a to the power 5, has been squared. Well, what would that mean? Simply a to the power 5 times a to the power 5. And by the first law of indices, we know we need to add the powers in this situation, so it must be a to the power 10. And if we go back and look at what we had originally, a to the power 5 to the power of 2, now we're not adding the powers. Surprisingly, perhaps, we are multiplying them, because when we expand it out, we see that is addition of the powers. But if we want to skip this step, we need this third law, which tells us we times the power when it's, if you like, a power of a power. So we can write this out algebraically as a to the power any number m. Put it all in brackets, and now put it to the power of any number n. Gives us the result a to the power m times n, and we call this the third law of indices when we're multiplying. Okay, so those are the three laws of indices, and they're pretty straightforward, and after a while they become very intuitive. Let's now move on to some interesting kind of spin-offs from this, because you might well be wondering about unusual numbers, unusual powers. And the first thing I want to think about is a to the power 0. Excuse me. Well, a to the power 0 we can work out algebraically by using the second law of indices. So if, for instance, I write a to the power, it could be anything, but let's say then a to the power m, and divide by a to the power m, you'll see why I'm doing this in a moment. So at the moment we're just looking right now we're just looking at the second law of indices. What would that be? That would be a to the power m divided by a to the power m. That would be subtracting those indices because of this division. So in other words, we end up with a to the power, sorry, hang on, let's just write this out like this. We end up with a to the power m minus n, but in this case it's not n, it's m, so they're the same. So we've got a to the power m divided by a to the power m equals a to the power m minus m, which is our a to the power 0. And if we go back to the beginning of our working here, we can see that anything divided by itself will give us 1. So we had that up here when we were working on these a's and using cancellation. So a to the power 0 must equal 1. So we've got our first interesting result. Anything to the power 0 is 1. So if you're working through an algebraic calculation, and we'll give some examples of these sorts of things later on, then whenever you've got to the power 0, you can replace whatever it is with simply the value 1, which is a nice handy thing to know and to work with. Okay. Next thing I want to look at is what happens if you have a negative power. So let's say we have, let's write it along here, a to the power minus m. Well, if we do some working here, again, if we work with numbers here, ordinary numbers in the index, if we had a to the power 2 divided by a to the power 5, we know that's when you subtract, and that's when you're going to get a negative. So you're going to have a to the power 2 minus 5, which is going to give us a to the power minus 3. Well, what does that mean exactly? Well, here, if we remember with our algebra, we had a to the power m times a to the power, this time, minus m. We, by the first law of indices, simply add the powers. So what would this be? This would be a to the power m plus minus m, or a to the power m minus m. Well, a to the power m minus m, as we've seen, is 0. So it means that a to the power m times a to the power minus m must equal 1. Let's write that out again. A to the power m times a to the power minus m equals 1. Sorry, I didn't finish that. There we go. Must equal 1. Because from our first result, we found that a to the power 0 equals 1. So that means that a to the power minus m, if I divide both sides of an equation, both sides of this equation by a to the power m, then a to the power m will disappear from this side, reappear on the other side, but as a division, it will end up as 1 over a to the power m. Okay, I hope you can see that. So all I've done is taken a to the power m over to the other side by dividing both sides by a to the power m, and we end up with a to the power minus m equals 1 over a to the power m. Now that's interesting because it means that whenever I've got this negative, I can replace it by 1 over the base to the power of m. So we get this sort of flipping going on when we've got a to the minus m. So if we go back to our summary that we're building up here, I'm going to rewrite this a to the minus m as simply 1 over, okay, as 1 over a to the m. And why this is so useful is because very often you just want to get rid of those negatives straight away. So you simply work through any algebraic expression, changing all the negative powers to 1 over 1 over the base to the positive power. So you've got rid of all of those negatives. So negatives mean 1 over. They're kind of flipping the base here. Finally, what happens if you have something like this? A to the power m over, let's say 2. Let's keep the numbers nice and simple. And we call these fractional indices because you've obviously got something like a fraction here. Any number over 2, well, it will be a fraction or a rational number. So fractional indices, how do we think about fractional indices? Well, let's think about what would happen if we squared this particular fractional index. So if we had this construction here, if we have a m over 2, so that's half m, you could say. So it's a fractional index. And by the third law of indices, which is what I'm going to sort of work with now, what would happen if I squared this? And you'll see why I'm doing this in just a moment. Well, what would happen is we would multiply. So the third law says we multiply in this situation. And we would be multiplying the m over 2 by 2. Well, that's going to make those 2's cancel. So we would simply end up with a to the power of m. So hopefully you can see that. The 2 would go would multiply the numerator, and we've still got 2 in the denominator. Then we divide top and bottom by 2, cancelling that 2, giving us a to the power m. Now if we have a look at this equation here, I think we can see that normally with an equation, what we would do when we've got a squared is we square root both sides. So let's do that now. So if we square root this side of the expression, the left-hand side, we'll end up with a to the power m over 2, or half m. So it was squared, now it's square rooted, so it removes that squaring. And on the other side then we must do the same. So we also square root this side, and we end up with a to the power m square rooted. So what that means is, and if I put a little 2 here, you should be able to see what's going on, that number in the denominator becomes a root, if you like. It becomes this rooting. So when we've got a number in the denominator, when it's a 2, it becomes a square root. Let's now replace that by a 3. Let's get rid of our working here. Okay, so if we had a 3 in the denominator, that then would be a cube root. Or if we had a 4, then it'd be a 4th root, and so on. So very often they don't make it that complicated, and if we're just working with ordinary surds, we'll often see this. The 2. But we can say generally that we've got a fractional index, which if we use just any general number here, so let's use the letter n, so one number divided by another number, then what we'll have is the square root, sorry, the n root, so whatever that is. If it's a 2, then it will be the square root, the n root of a to the power m, because that number in the numerator is simply going to be a power, so it's going to be squaring it or cubing it or whatever. So we have this. So there are our 3 general principles, if you like, or theorems perhaps, that we're working with. Now let's look at some examples and see how these things help us to solve real problems. So let's, for example, say they ask us what to rewrite something very simple. Let's say 2 to the negative 2. Well, immediately I want to get rid of that negative, so by this second principle here, I flip it so it goes 1 over, and then I rewrite the base, and now it's simply squared like that. And so that's the rewritten expression here in a more familiar form. Let's do another one. Let's say I had, so let's call this A. Let's have a B now. Let's say I had, let's say half. Make it a little bit more complicated. To the power minus 3. So what I'd have here is 1 over, so immediately deal with this negative index. So I'll have 1 over a half. I better bracket it so it's very clear that this is now being cubed. So all of it's being cubed. And if I cube a half, then I'll get an eighth. So it's 1 over an eighth, because I cube both the top and bottom. So cube the 1 and I get 1. Cube the 2 and I get 2 times 2 times 2, which is 8. So I've got 1 over an eighth. Well, 1 divided by 1 divided by 8 is simply 8. So I flip it twice if you like, and I end up with 8. So my answer is 8. So a half to the power minus 3 equals 8. Let's do another example. So C. Again, working with these negatives so that we get familiar with that. Let's have a negative number to the power, let's see, minus 3, let's say. So now that would be 1 over minus 5 to the power 3. Again, let's just bracket it so we're clear what we're doing here. The brackets tell you basically that it's negative 5 first, so you're not cubing 5 and then it's a negative. So it's minus 5 to the power 3, or minus 5 cubed. Well, minus 5 cubed is going to be minus 5 times minus 5 times minus 5, so it's going to be 1 over minus 125. And there's our answer. Minus 1 over, let's just rewrite it, minus 1 over 125. Okay, negative 1/125th, if you like. Okay, let's do one final thing. What if we had something like 7 to the power of a fractional index? So let's look at these fractional indices now. But let's put that in the negative like this. Well, that would simply be, again, deal with this negative first. 1 over 7 to the power half. And we know that to the power half means square root. So we end up with 1 over the square root of 7. Okay, maybe just a couple more. Let's have a think. If we had, let's do something a little bit more challenging, the sort of thing you might get in a quite kind of tough-looking GCSE question. So if we had something like 27 divided by 8 to the power, let's say a third this time, because we often do a half. Let's say to the power of a third. Then what must that mean? So simply a third means cube rooting this time. So we do the root sign, and we put a little 3 here to say, well, this is a cube root. You get this on a calculator, so you can do cube roots on a scientific calculator. And it's reversing, if you like, cubing, the cubing operation. So now we put the 27 divided by 8 underneath. And I deliberately chose these numbers, of course, because they're easy to cube root. So that's going to be the same as the cube root of 27 divided by the cube root of 8. And now if you're not sure how I can do that, just check out the surds video where we'll look at those kind of operations where we're now rooting both top and bottom. And then we can resolve this. The cube root of 27 is simply 3, because 3 times 3 times 3 equals 27. And the cube root of 8 is 2, because 2 times 2 times 2 equals 8. So we end up with 3 over 2, or 1.5. Okay, well, I think that's enough for this video on these ideas using indices. But in the second part of the video, I'll look a little bit in a little bit more detail about where these ideas come from, and particularly the idea of the logarithm. Okay, so in fact, let's just focus on this idea, this word, the logarithm. People get very confused what it means. It used to mean an awful lot more than it did, because it was a very important tool for calculation, and people before the calculator used to use logarithms to solve all sorts of problems. So you really needed to be skilled in logarithms. Now these days, really, because of the calculator, we don't use logarithms nearly as much, and it's almost gone from sort of GCSE level mathematics. However, you may come across the term, and it's useful to know what it is. So if I look at the dictionary definition here, it says a logarithm in maths is the power to which a fixed number, or a base, so here's our base, the a here, any number a, the power to which it has to be raised, so that's the x here, to produce a given number. So that would be that y. Okay, so it's when we use the idea of a logarithm when we want to find out what the index is. And so if I give us a sort of more detailed definition here, we've got x here. X is the power to which a must be raised, okay, in order to give the value y. And that's basically the definition of logarithm. That's what logarithm means. So it's a strange word, traditional word, used to describe how we rearrange things to ask ourselves, well, what actually is x here? And we write it like this. So we've got x equals the log of y to the base a. So we say it like this: x equals the log of y to the base a. And there's the base. Now it's gone in subscript here, and we use this shortened form of the word logarithm, log of y to the base a. So how does this work in practice? Well, the only thing you're likely to come across is something looking a bit like this. So if I keep it nice and simple, we might have the log of 32. So keep the numbers that we had before. The log of 32 and to the base of 2, to the base 2. Okay? So what's this saying? What's it asking? It's asking us to find the log of 32 to the base 2. What does this actually mean? Well, if we just say, well, the answer that it wants here is x, that's what we're trying to find. Let's then rewrite this in terms of x. So we take the base, so here's the base here, and write it normally as a normal ordinary number. And we put x as the index. So that's what we're trying to find. This is what this is asking us for. So it's 2 to the power of what will give us this number, 32. Now that's got rid of this horrible log and simply expressed it in exponential or indicial form. And so now we can ask ourselves, well, how do we solve this? Okay, well, what we have to do before we can solve this is make sure that the bases here are the same, left and right. So 32 is in fact 2 to the power of 5, as we saw in the video. So in the earlier part. So we can now rewrite this. 2 to the power x gives us 2 to the power 5 equals 2 to the power 5. So we've now got the bases equal. We can see very clearly now that x then must be 5. If 2 to the power x equals 2 to the power 5, then x must be this number here, 5. So our solution is x equals 5. So log of 32 to the base of 2 equals 5. Okay, let's do one more so you can see how this works again. Maybe you can pause the video and give this a go yourself. So we've got log, this time of 81, let's say. And I'm going to put this to the base 3. So it's log to the base 3, log of 81. So we usually do it in that way. Log of 81 to the base 3. And what's the answer there? Okay. So what we do again is we take our base, so we sort of translate this into, get rid of this logarithm language, and instead say, well, we got, oops, not 2, but 3 as our base then. Okay, so 3 as our base, and the missing number that we want to find is x. So we've got 3 to the power x equals what? Equals 81. So, how are we going to solve this? We need to make sure the bases are the same, both sides of the equation. So we say now 3 to the power x equals 3 to the power, well, 3 squared would give us 9, 3 to the power 3, or 3 cubed would give us then 3 times 3 times 3, which is 27. So 81 is 3 times 3 times 3 times 3, in other words, 3 to the power 4. So you can check that, but it's just a kind of reverse operation. So we've now got 81 is 3 to the power 4. So 3 to the power x equals 3 to the power 4, then, so therefore, x must equal 4. So log of 81 to the power 3 equals 4. Okay, so that's just some extra sort of thing that you might come across in an exam paper that you ought to know about, and it simply is another way of thinking about these indicial or exponential equations.